Everybody, today we'll be talking about design of unreinforced walls under both out of plane and vertical loads. As you know from previous lectures, almost all of masonry walls are either non-load bearing or vertical loads only. However, in some cases we have both together. Maybe out of plane being the main player or vertical being the main player, depends on the case. However, if you have high winds or you have earth retaining walls or tanks, in such a case, in such cases, the lateral loads will be the lateral out of plane. Sorry, not lateral. The out of plane loads will be the main plane. So, as we know from previously, the out of plane shear, according to the code, the allowable out of plane shear is 0.08 root f dash m, which is less than or equal to 0.3 megapascal. The shear stress is equal to Qs over Ib, and I need to mention something here, that there are two equations in the code, not only one equation, which is, I know it's something causing a lot of confusion for some people. So this is one of the two equations giving the value of shear, which is the shear force multiplied by the first moment of inertia divided by the moment of inertia and the effective width. The other equation is simply the shear divided by the area, which is B times D. So there are two equations and both are mentioned in the code for the same thing, okay? Which gives you the alternative that you could use either, actually, okay? And this Q should not exceed 0.5 megapascal, 0.125, the least of 0.5 megapascal, 0.125 F dash M, and nu plus 0.35 N over AN, where nu is 0.08 megapascal in case of stack bond, 0.2 megapascal in case of ungrouted running bond, 0.32 megapascal in case of grouted running bond. Taking us to normal stress, you will do the checks that we have done for normal stress typically. So we'll do the design for bearing, in which the bearing stress is equal to 0.25, the allowable bearing stress is 0.25 F dash M. The axial compressive stress is FA, which is equal to P over AE. The bending is plus or minus My over I. However, the new thing here is that this M, the source of this M, is what you have from the bending moment diagram, the most critical value, plus or minus, depending on the direction, the moments due to eccentricity. So whether it's a plus or a minus, it depends on the direction of the eccentricity relative to the direction of the bending moment from the bending moment diagram. So you could be acting both together, or one will be counteracting the other. So it depends on the case. It's a case by case thing. You need to be very careful when dealing with something like that. And to guarantee that no tension failure happens, by the way, this is a type here. It's not tension. It's not tension. You are allowable to have tension in such a case, but we are not talking about no tension failure. To guarantee no tension failure to happen, the word failure is missing here. The FB should be less than the value mentioned in the table code, the table 3.1. And of course, FA plus or minus FB should be less than FBR. And again, the bearing stress is only checked if you are having a bearing failure. So if you are having a load resting on a plate above the wall and the load is not distributed, the load is concentrated. So in such a case, you are worried of bearing failure. However, if you are having a distributed vertical load from the beginning, you should not check for bearing from the first case. I mean, you don't need to check for bearing. And if you are talking about a distributed vertical load, so you don't need it. Here we are talking only about a concentrated vertical load. Okay? So that takes us to stability. Stability, which is actually the normal stresses that you are checking, that the normal stresses will not cause failure. So small FB over capital FB plus small FA over capital FA. This is, or the summation of that stuff is less than 1. This is exactly like what we have talked before. The same FA, the same radius of gyration, the same rules apply, where FA is equal to 0.25 F dash M times 1 minus H effective over 140 R whole square. The allowable strength FB is F dash M over 3. For buckling, the same critical buckling load PE is equal to E times I over pi times pi over H effective square multiplied by 1 minus 0.557 E over R whole cube. However, this E, the eccentricity, is the original eccentricity due to an eccentric vertical load. So if the vertical load is concentric, even if you are having a bending moment due to a bending moment, a lateral load coming, this E is equal to 0 if the load, the vertical load is concentric, whether you are having an out of plane bending or not. Okay. However, if this load is eccentric, you will place the value of the eccentricity, and the axial load is equal less than or equal to PE over 4. And this is the table that discusses that shows the values, the allowable values for the tensile stress. And again, this case is where you are talking about an out of plane bending. Okay, whether this out of plane bending comes in combination or with vertical loads or not. However, if you are having a vertical load only without out of plane bending, the allowable should be 0. The allowable tensile stress is 0. Okay. However, if you are having an out of plane bending, the code allows you to take these values depending on the mortar grade and depending on the type of bond and the type of masonry units you are talking about. So let's take a nice example here. We'll check the safety of a fence made of solid cement bricks, 60 mm by 120 mm by 250 mm. If the wall height is 3 meters and the thickness is 250 mm, the wall is subject to a wind pressure of 2 kPa with a vertical load of sorry, this is a typo here. The vertical load is not 10, it's 5 kN per meter. Okay. Consider the mortar to be of type 1 megapascal, pressure strength of bricks to be 15. So from the table 212, F-M is 5.4 megapascal, Q allowable is 0.08 times root 5.4, which is 0.186, and FB is F-M over 3, so this is 1.8 megapascal. So Q is equal to 2 times for a 1 meter strip. Of course, we'll do all our work for a 1 meter strip because the vertical load is distributed and the wind is a pressure. So we'll take a 1 meter strip and base our design on it. And by the way, we forgot to mention here that this thing is considered to be simply supported because you're having a beam at the base, a ground beam at the base, and a vertical and at the top of the wall you have a lintel or another RCB. So and the distance between them is 3 meters. So the Q is actually the reaction, which is 3 kilonewton, 3000 newtons. S, which is the first moment of inertia, is the distance, is the area times the distance from the centroid. So it's 1000 times 250 times 125. So this is 3125 and 4 zeros millimeter cube. I is equal to 1000 times 250 cube over 12. And the value will be comparing to 0.125 root 5.4. This is 0.291 megapascal. So Q is equal to Qs over I times V. So this will give us 0.072 megapascal, which is less than Q allowable. So therefore it is safe and shear. M is equal to 1 times 2 times 2 square over 8. This is 1 kilonewton meter, which is 1 million newton millimeter. So then multiply this number by y over I, you will get 0.096 megapascal, which is less than the allowable the allowable bending value. So this thing is guaranteed to be safe in tension due to bending action. Okay, so this is safe to in tensile bending stress. For a 1 meter strip, again, we will do now work on the axial load. So because we are having a distributed vertical load, we don't need to check bearing. However, we will check the axial load. So Fa equal P over A. So this is 0.02 megapascal. The radius of gyration is root I over A. So this is 72.16 millimeter. Fa, if we apply the equation, we'll find that Fa will be, capital Fa is 1.23 megapascal. So now we'll do our stability check. Small fb over capital FB plus small fa over capital Fa. This will give us a very small ratio, which is 0.07, which is less than 1. So we are safely safe for normal stresses. On the other hand, we'll check the buckling. So EM is equal to 900 F-M. So 900 times 5.4, this is 4860 megapascal. You multiply this number by I and by pi over h effective square. And since we have zero eccentricity, the load is concentric, the vertical load is concentric. We are talking about 72. The last term will not have an effect on us. So this will give us an axial capacity, an Euler buckling load of 6940 kilonewton. And of course, when you divide this number, this very large number, by 4, it's significantly much larger than the 5 kilonewton for the 1 meter strip that we are talking about. So this thing is again safe for buckling, and that's it for this time. Thank you.